Hey everyone, welcome back. In this video, we're going to look at another example of solving one of our larger 3x3 systems of linear equations. And so in this system, our first equation is x plus 2y minus z is equal to 4. What we're going to call equation 2 is 3x minus y plus 2z is equal to 3. And our third and final equation that makes up our system is the equation 2x minus 3y plus 3z is equal to -1. And so our first task here is to take our 3x3 system and reduce it to a 2x2 system. Remember, the way we always do this is by taking two different pairs of our three equations and eliminating the same variable from each of those two pairs. And so now we have to scan our equations, the coefficients involved, maybe do a little bit of mental arithmetic, and decide which variable do we want to eliminate here. And honestly, for this example, it looks like any choice is going to work out with just about the same amount of effort, whether we want to eliminate x, y, or z. It doesn't really matter here. I'm going to go ahead and make an executive decision and say, let's go ahead and eliminate the variable of z. What helped me make this decision was I have a -1z in the first equation. So if I multiply that by 2 and add it to the second equation, that'll be an easy way to eliminate the z's between those pairs of equations. Or I could multiply the first equation by 3 and add it to the third equation, and that'll knock out that 3z in that third equation. So let's go ahead and reduce this to a 2x2 system by eliminating z. All right, so the first pair of equations we're going to work with to eliminate z are equations 1 and 2. That makes up a pair. We're going to multiply equation 1 by 2, so that becomes a -2z. Everything else will get affected as well, but we're focusing in on the z's because that's the variable we want to eliminate. So that'll make it a -2z. So when we add it with the positive 2z from the second equation, the variable of z will eliminate itself. So let's go ahead and write all that out in all the detail. So 2 times our first equation is going to look like 2x plus 4y minus 2z is equal to 8. And our second equation is not changing. It's still 3x minus y plus 2z is equal to 3. So if we take the sum of those two equations, add the left-hand sides together as well as the right-hand sides together, it looks like we end up with 5x plus 3y on the left-hand side, and that's going to be equal to 11 on the right-hand side. Let's go ahead and call this equation 4. So this is going to be the first of our two equations in our 2x2 system. Our 2x2 system should only involve x and y at the most. And so now we need to use a different pair of our original three equations and eliminate z from that pair as well. Let's go ahead and use that combination I described earlier, where we're going to take 3 times our first equation and add that to our third equation. That should get rid of z between those pairs. All right, so multiplying our first equation by 3 turns it into 3x plus 6y minus 3z is equal to 12. Don't forget to multiply the right-hand side. It's probably the most common mistake I see when looking at people's work on these problems. And then our third equation, just copying that down, we got 2x minus 3y plus 3z is equal to -1. All right, so now we got to add these equations together. Adding the x's up gives us 5x. Adding the y's up gives us a positive 3y. The z's cancel each other out, and that's equal to the right-hand side of 11. And we will go ahead and call that equation 5. But now if we take a step back and look at equation 4 and equation 5, what we should notice is that they are the exact same equation, right? 5x plus 3y equals 11. And so if we're thinking about being in 2 dimensions, which we can do since we've reduced our system, these are the same lines, or if we were in 3 dimensions, the same planes, but we're not too worried about that at the moment. So these 2 lines are going to coincide or land on top of each other, and that's going to give us infinitely many solutions. If we did not observe that right away, just by noticing the equations are the same, we'd still run into it algebraically, because what's our next step after finding our 2x2 system? It's solving that 2x2 system. And well, how would we solve our 2x2 system here? Well, we probably just subtract equation 4 from equation 5, or equation 5 from equation 4. They're the same, so it doesn't really matter. But either way, when we subtract those equations, we're going to see that every single thing cancels out, giving us a true statement like 0 is equal to 0. We don't need to identify the exact geometry of what's going on causing these infinitely many solutions. We just need to recognize that there are infinitely many solutions.